Hello everyone, welcome to another video of mine. My name is Nnamdi. Today we're gonna try to talk about DRAM. OBINexus DRAM. DRAM stands for, it's not a DRAM. It's an active memory system for RAM. It's like if it is not DDR3, it's not DRAM. It's OBINexus RAM in silicon. You know, it's meant to be in silicon. But you know, if you go to github.com/OBINexus DRAM, that is the DRAM exists as an exe file or like an executable. When you make it, would make. It is written in C, but you know, as an MVP. But you know, github.com/DRAM is written in C. Okay, so what's the problem? So DRAM is a memory cache. It's RAM. DRAM stands for Directed Instruction RAM, or Random Access Memory. It's an active memory system that allows active eviction of states. The problem with traditional architecture is that DRAM or Directed Instruction RAM solves is that it treats memory as active, not passive. We have like in your computer, you have a silicon. We have DDR3. DDR3 active passively allows for caching, which is the main feature of a RAM system. So able to store caching or store information such as LRU caching and cache hits, cache miss, and update the system. But DRAM is inspired by the concept of directed evolution, based on next search principles, searching for with the searching. So how DRAM works in hardware? It's in how traditional DRAM systems works. For this traditional system, they are passively storing states and transitions and caching it. So if you implement a list using cache system to evict most used items, MRU systems, you know, that is a priority queue and a heap structure to prioritize the most least used item. You know, the things you use less. You know, things you may forget, which the cache system stores in memory. And that's the problem. Or if you have an MRU cache, or TTL cache, or something that's time to live. TTL stands for time to live. You know, a cache system that only caches what is needed when only deletes a cache later, say in 30 days or something like that, which is time to live cache implementation. It will allow you to evict the data with a weak map or with a weak something weak in memory, and then destroy that data. MRU cache, MRU can store the most recent item, and then LRU will remove the based on the heap implementation using a priority queue. To implement a heap, to shadow how the system orchestrates information based on the needs. But in a passive caching system, you cache hit and you cache miss. You know, it stores every state and transition, and you keep on caching passively. You know, you use the RAM, you store here, and you cache it, or cache it, or cache it. It doesn't care about whether the data is how the data. If it does something, it doesn't really care about it. So how does RAM? So DRAM flips the script on this. So what DRAM does is it allows you to cache when you need it and remove the stuff. So if you have an implementation of an AU cache in C or Rust, DRAM.exe first uses the Unix compliance implementation of a linked list to or the DRC or the DRC DRAM.exe, which you can pass to DRAM.exe-c and some flags DRAM.exe to do DRAM.exe. When you built it, of course, when you build the binaries, and then this will be when you put the ampersand at the back of the system or the post indentation, you are then making sure that it's running in the background. But you know, you don't have to do that directly. You can just use the detach mode to detach it from the system, and use kill-9 the PID for the process, which will show you. But you know, when you run DRAM.exe, you are really using the RAM-c detach DRC, which is a configuration system, to configure how that system allows you to command system how many memory allocation, what is what. So what is used. So when you look at the ARE cache system, the two main issues, how the DRAM works is it uses something called a XOR gate and a CNOT gate. If you have if you check it, the math, use all logic gates, So when there are two channels, two inputs and one output, so you have like an XOR gate, which is like which flips it. So you got is it an OR gate? Yes. So you got an XOR gate which flips the bits. So if you have 0 0 and you have XOR, it opens the electric flow in and electric flow and then closes that and then it's done. It closes it. So XOR flip a 0 to a 1. And then let's try to you have a 0 again. Two inputs are 0. So the four states are 0 0 0 1 1 0 and 1 1 respectively. And the XOR gate will be 1 0. 0 1. So you have 2 0 0 0, and then the XOR gate you get the go through XOR, which is exclusive OR. So you go to 0 and it gets equals to 1. The CNOT uses quantum rotation of the same system, which is for quantum computers, because we're really trying to build this DRAM architecture in silicon using working memory model. Okay, so I'll come back to working memory model in a second. So you got XOR, CNOT, and CNOT has two inputs, which is like for quantum computers. So that input, with a classic system, will just go to XOR, and then you can get a CNOT gate. Without CNOT gate, say there's no CNOT gate, then you get a 0. So you get then the O will run. Exclusive O. So you get O, O 0 or 1, the 1 on 1. So that's 1 on 1, and then XOR will be 1. 0 0 will give you 1. If you have 1 0, you get 1 in inputs, O, and then you flip that input, and that's 1. You see, because you get 1. So what this RAM architecture does, it just preserves the state passive actively. In the silicon on the RAM system, it actually preserves the hardware. You can have like for all states 0 1 1 0. If there's a 1, it keeps that 1. If there's a 0, it keeps that information basically. It retains all the information for the bits, for the bytes of data. A byte, so you have A bytes or triplets, we can compute that. It will give you that output of that triplet, as it is. But it will retain, because it doesn't really forget. It can't forget. It just retains the information, and it's adapted for quantum computation too. It allows you to compute, keep the information in case a component system degrades. Something get error from somewhere. And that's what the DRAM system is actually doing. DRAM.exe is a revolution. You guys change everything for quantum computing. I want to introduce you to the working memory system for AI. If you know the GitHub, if you know the ontological Bayesian infrastructure for AI, which is a system, how this fits into DRAM in the greater sense is DRAM.exe allows you to directly random instruction memory to using something like a filter flash model of cognition. Filter meaning objective memory. Filtering means objective searching, searching objectively what everyone knows. A flasher means storing. You can start storing objectively knowledge, based on your current understanding or your hypothesis, your observation, what you make up. Your relativity. And then the filter flash memory architecture, thinking of filter again. So how DRAM does this for AI systems, which have ontology-based infrastructure, meaning ontological meaning knowing how you be who you are, how I be who I am to be. It means it's a philosophical question that means, how do I know who I am? How do I know I am Nnamdi? Or how do I know you are you? Without too much guesswork, my life, my story, who I am. That's the meaning of ontology. It's a state of being. Who are you? Who is Nnamdi? Who is God? Who are you? How do I know? So the ontology-based infrastructure for AI system uses filter flash model to map to filter and flash. Filter means objective or subjective reasoning. Filter means filtering information, and then filter means objective, subjective, and then you got the flashing, which means to store information. Remember what you gain from that knowledge, what you've stored, how you understand it in me. based on epistemically cost function. I'll go back to that for OBA, but I'll go to another video. I'll go to the if you go to epistemically cost, I'll make a video on that too. Yes, so we got that. The working memory here is a thing in memory that's actually. Oh man. Yes. So the working memory. Oh my hand is not. So the working memory is the thing in memory that's working, currently being processed. We got the flashing and the filtering, which refers to the intersteps. So if you have like a filter, which is the DRAM process, you go down the flash, filter, flash. So that means flashing means storing first, which is subjective knowledge or objective solution, what you already know. And then you go to the filtering stage. How do I transform this data to gain using KNN clustering to give it some flashing, to store it again to help the user when the user gives a prompt. So DRAM is a working memory architecture for directed instruction RAM, directed instruction memory that persists. So when you have a caching strategy like LRU to store something, you can cache anything you want, but you use it actively because it stores what you need. The way you want to really optimize algorithm, that's what it works. Because if you really get into this DRAM, if you really love DRAM, and you want to really optimize, I suggest you implement. Implement your own caching system. Caching LRU, MRU, and with your Hebrew structure, what you're trying to cache based on what your context. And then you use cache hit and cache miss. So because DRAM supports that naturally. So if you have a cache hit, you can understand that before your cache gets evicted, there's a process. A cache hit means the data, the model, your system needs an update. Whatever you're storing needs an update to cache. Say you have someone have a new change in the data. It caches that you trigger a cache hit. A cache hit will allow you to cache on events as a policy to cache more. To handle the update accordingly, build the user on an application or something. Yes, so that's what it does. So the cache hit is very important. You can trigger caches. If you want to balance in a cache hit and cache miss, or if you're trying to maximize one over the other based on what you do, DRAM can use that for specific use cases. A cache hit can trigger more updates per cache strategy. That's LRU, MRU, TTL. Before being evicted or being removed or being not cached anymore. And then a cache miss means that there's no update trigger. Maybe it's an error or an exception, the system overlooked, or your caching system implementation overlooked. But it can be a bit error, an exception, or pilot state. But when you're writing in C, you can include DRAM.exe into your code file and start using the DRAM utility. Imagine this. Imagine imagine like a RAM architecture that uses token type, token memory, token value, a new structure to allow for DRAM to trace the memory acquisition of assembly artifacts. Because it works for compiled languages only. An assembly is compiled too. One really invention for DRAM is to use it for assembly to ensure that memory traceability in the system, across assembly artifacts and components and executable for that target platform or program. So remember, DRAM. Welcome to okay. This is OBINexus Nnamdi signing out. Computing from the heart. Like, share, and subscribe, and check out the minimum viable product on DRAM. I believe I'm having some issues now with it, but you can find one that is like stable too. Yes. Okay. Thank you. Goodbye. So share, like, this super video. Thank you, and share it. Okay. DRAM.exe. Nnamdi signing out.